Opening a chest in a video game is designed to look like pure chaos. You crack the lid, and a fountain of gold, weapons, and junk spews into the air in a completely unpredictable spread. To the player, the outcome feels entirely random and highly volatile. But the designers building these systems do not rely on chaos. They rely on rigid mathematical abstraction. Look at these static dice. Before anyone ever rolls them, we know exactly how they will behave mathematically. This equation illustrates theoretical probability. It is calculated by dividing the number of favorable outcomes by the total number of possible outcomes. For a standard die, the theoretical probability of rolling a specific number is 1 in 6, or 16.67%. That 16.67% represents a mathematically ideal expectation. It assumes a perfectly balanced die, rolled an infinite number of times. But humans play in short, contained sessions. The actual observed result of a specific sequence of attempts is called experimental probability. If you roll a physical die 50 times in the real world, you might roll a 4 8 different times. That yields an experimental probability of 16% for that single session, missing the theoretical mark. Theoretical models simply do not account for the short-term volatility of chance. In small sample sizes, the observed results will frequently deviate from the mathematical expectation. Game developers do not try to fix this discrepancy. They actively exploit it. The strict mathematical probability dictates the macroeconomic stability of the entire server over months and years. But the short-term experimental volatility generates the emotional highs and lows of an individual player's gaming session. To manage both realities simultaneously, modern game engines do not simulate simple die rolls. They use nested algorithmic architectures, known as loot tables. This animated diagram demonstrates how game engines discard flat physical dice. Instead of a 6-sided cube where every face is equal, software logic uses independent arrays called loot pools. Inside a pool, outcomes are represented as a segmented bar chart of numerical values, known as weights. An item's drop chance is no longer a fixed fraction, like 1 in 6. It is calculated dynamically by dividing that item's specific weight by the sum of all viable weights currently in the pool. We can observe this weighted architecture executing in Minecraft's desert pyramid chests. If the total accumulated weight of all items in the pyramid pool is 247, and a diamond is assigned a weight of 5, the theoretical probability of selecting a diamond on a single algorithmic roll is exactly 5 divided by 247, or roughly 2%. Developers can also assign a weight value to an entry labeled nothing. When the algorithm selects this specific weight block, the system intentionally fails to generate any item at all for that roll. This forced failure mechanism prevents every chest from being filled to capacity. It allows designers to control the pacing of rewards and avoid oversaturation of the game's economy. Furthermore, a single chest can contain multiple distinct loot pools that operate autonomously from one another, generating common resources independently from rare artifacts. By replacing equal odds with static weights, designers secure the tools necessary to establish the macroeconomic rarity of every item in the game. This code structure is a JSON file. It serves as the literal blueprint where theoretical math is written directly into the game engine. The engine executes this file sequentially. It begins by establishing the root object, which defines the overarching parameters for the entire table. Next, it declares the pools array. Because it is an array, a single JSON file can trigger multiple independent loot pools simultaneously. Inside a pool, the rolls command instructs the engine exactly how many times it must pull from the defined list of items. Finally, the code defines the entry providers. These dictate the specific item IDs to be generated when a given roll successfully selects their assigned weight. Older, primitive game engines hard-coded fixed item drops directly to enemies or containers. If you defeated a goblin, you received a goblin sword. This modular array-based architecture allows the engine to continuously generate dynamic, unpredictable outcomes that maintain infinite replayability without altering the core source code. However, pure static probability lacks situational awareness. A static table does not know if a player defeated a monster with a sword, or if the monster simply fell off a cliff. To solve this, the engine generates a loot context. This is a millisecond data snapshot capturing the exact state of the game environment the moment a generation event is triggered. This flowchart demonstrates how parameters are fed into that context snapshot. Variables like the damage source or the specific tool the player was holding are packaged together and sent into the loot table's logic. The table then uses conditions. These are strict logical gates that evaluate the incoming parameters before an item can even be rolled. If a contextual parameter fails the condition check, for instance, if the entity was not killed by a player, the target item entry is entirely discarded from the pool before the mathematical weights are calculated. Developers can also introduce secondary player attributes, such as a luck step. This dynamically intersects with the baseline item weights using a quality modifier multiplier, mathematically inflating the relative weight of rare items. But this requires precise mathematical balancing. If designers assign high-quality modifiers to common items, they will invert the rarity curve. As a player's luck increases, the common items would gain so much weight that the rare items become mathematically impossible to acquire. When calibrated correctly, conditions and modifiers transform rigid probability tables into highly responsive, context-aware economic regulators. Dropping a single, fixed quantity of an item every time quickly feels mechanical and repetitive to a player. To fix this, loot tables use number providers. As shown in this diagram, these are dynamic mathematical functions that replace flat constants with distinct distributions. The first shape is a uniform distribution. Here, you define a minimum and maximum threshold. Every quantity between those two numbers has an exact equal chance of being selected by the engine. The bell curve represents a binomial distribution. This calculates successful outcomes over multiple independent trials, creating a specific, weighted clustering of numbers. It makes moderate drops common, and extreme high or low yields incredibly rare. Applying these advanced probability curves to roll amounts ensures the volume of items feels organic to the player, while remaining strictly bounded by the developer's underlying math. Despite all these granular JSON components, an individual player opening a single chest will still experience wild, unpredictable fluctuations. The ultimate mathematical safety net for the game's economy is Bernoulli's theorem, commonly known as the law of large numbers. This simulation illustrates the theorem. On the left, 5 trials yield chaotic results. On the right, aggregating 10,000 trials smooths the output to match JSON weights. Over millions of cumulative trials, experimental outcomes inevitably converge with the theoretical design. The nested JSON pools, strict parameter logic, and binomial number providers are the mechanisms developers use to enforce this theorem on a server-wide scale. Mastering this stochastic architecture allows developers to guarantee a stable global economy while preserving the emotional thrill of the unpredictable drop for every individual player.